Hey everyone, what's going on? Let's take a look at everything from our Unit 1 of statics. So this will be the first test that we cover. Um, so, what have we gone over so far? So, we did an intro to trig. That was more review than anything. We started introducing particle physics. Which is what our test is going to be on, right? We mentioned that we're working only in 2D and only really working with one point of application, or like the forces are only applied to one single point. What that means is, like, let's say we had a car. We would represent that car as just a point. So instead of being like, hey, this is a car, and each tire has some series of forces. There is drag all along the car, right? Instead of looking at, there's a driver who's going to be an individual person, pretend that's a person, driving a car, and so they're going to create forces on the steering wheel, and there's going to be all types of interactions in the hood of the car, in the back, underneath, in the engine, the axles, everything, right? We're not looking at that. We are looking at the car as if it were a point. So we would be looking at, so for in the case of the car, we'd be using the center of mass as the point that we're evaluating, right? We didn't spend a lot of time talking about this. It's just that things can be reduced to a point to simplify our problem solving process and to estimate. So let's say we have this car. This car has a weight, so that's now a force. There's a force of drag. The car is moving in this direction, which means there's a force pushing the car, a force that the car is creating against the road, but it's going to push us forward. So the force of movement, say. So only 2D forces and only applied to one point. We did do a mix about talking about systems in equilibrium and systems not in equilibrium. Both of those two elements will be covered on the test. Okay, so with our particle physics, let's say, yep, no equilibrium and equilibrium problems. Okay, so with our, oops, how do I get back in here? Okay. Okay, so for our no equilibrium problems, we looked at, let's say triangle rule 1, parallelogram rule 1. What else did we do? And the XY component method. In cases of equilibrium, we have the same kind of set of things, but we're going to call them a little bit different. We'll call this triangle rule 2, parallelogram rule 2, and let's just add, we'll say XY component method not equilibrium and XY component method in equilibrium. Okay. So let's start by focusing on situations that are not in equilibrium. To do that first, let's define equilibrium again, right? I think we did that in one of our earlier classes. Let's just do it verbally. So let's not do it verbally, actually. Let's write it down. So let's start talking about those equilibrium situations. So equilibrium is when the summation of forces are all equal to 0. So if we see any notes about something is stationary, something is not moving, holding still, whatever the case may be, that tells us that it is in equilibrium. Likewise, this is something we've not seen a lot of yet, but if we were to have, if it were to have a consistent acceleration, meaning, right, so F equals ma. So if acceleration is equal to 0, then the summation of forces is going to be equal to 0, even if velocity is not equal to 0, right? So it doesn't technically have to be holding still, but our equilibrium condition is when our summation of forces is 0. So, for our equilibrium triangles, so let's start with our first method, is triangle method 1. So for triangle method number 1, we're going to have 2 component vectors or component forces. And we're going to have 1 resultant of those 2. Okay. For the triangle method, so let's say for triangle rule and parallelogram rule, regardless of which situation you're working on them with, you're going to end up with 2 diagrams. One is going to be your space diagram. Let's not call it a space diagram. Let's call it a free body diagram. Your first is going to be your free body diagram, which is going to be based on the scenario. We'll say FBD for free body diagram. And the second diagram you're going to need is either your triangle or your parallelogram. I'm just going to draw a parallelogram. You know what I mean, right? Okay, so, oops. How do I unselect it? Okay, so for our triangle rule number 1, our 2 component forces. So let's give an arbitrary free body diagram, right? So that's going to be the point of application. Let's do a positive x-axis, a positive force in the y-axis and a force in the positive x-axis. Okay, so let's move that into a triangle. So for our triangle rule, we're going to start with either force. So let's say this is F1 and this is F2. I could go F1 and then F2, or I could go F2 and then F1, as long as I am connecting them head to tail, tail being the non-pointed end of the vector and head being the pointed end. So the direction or the sense of direction, right? Our resultant force is going to be not on our free body diagram, but it is going to be in our triangle. And it is going to oppose the direction of the other forces. So it is going to go from the tail of the first to the head of the second. To the head of the second. From the tail of the first to the head of the second. Do you see how regardless of what order we put them in, they still, the resultant still ended up being in the same direction, right? It ended up still looking the same. So our forces, our component forces are going to go in one direction, either counterclockwise or clockwise. So in F1 to F2, we have a clockwise direction, and F2 to F1, we have a counterclockwise direction. Our resultant force is going to oppose that. So in this case, we have a counterclockwise direction, and in this case, we have a clockwise direction. Okay, for our how do we scroll down? Struggling. Hold on. How did I do that before? Okay, zoom out and then zoom in down here. I don't think that was the easiest way, but we'll figure it out later. Okay, part 2, or the second element of that, is going to be using the parallelogram rule. So this is going to be the same type of thing where we're going to have two component forces. It's just another method of getting the same type of idea. Just instead of connecting head to tail, what we're going to do is we're going to take our point of application. So this would be our free body diagram right here. And now I'm going to work on our triangle that's going to get us the geometries that we're going to work with, okay? So here we're going to have both of our component forces coming from their point of application. And then what we're going to do is we're going to draw parallel forces. So let's draw a force parallel to F2 at the head of F1. And let's draw a force parallel to F1 at the head of F2. So now we are going to connect from the point of application to where those parallel lines meet, and that is going to be our resultant force. Okay? So if you're using the parallelogram method, you're going to end up with two triangles that are essentially equal to the two triangles that you would get using the triangle method, okay? So the geometries are going to line up, so you're going to be able to use the same set of equations. So what equations did we use with our triangle and parallelogram rules? So the first one would be our law of cosines. We focused on one form of the law of cosines, which would be to solve for the resultant force. So the version of the law of cosines we focused on was r squared equals p squared plus q squared minus 2pq cosine beta. What does that mean? If we don't know what these variables mean, it doesn't mean anything, right? So r is going to be our resultant. So on our triangle, it's going to be the hypotenuse, which also I'm not positive how to spell. P and Q are going to be the component forces. And B, or beta, depending on my mood usually, is going to be the angle opposite R. I mentioned briefly in class that we could change the format of this law of cosines. We could we could switch the place of one of the resultant force and one of the component forces. So in other words, we could have P squared equals R squared plus Q squared minus 2RQ cosine, and then let's say alpha, as long as alpha is opposite P. Okay, so this isn't exclusive to just the form of the equation that we have above with R separate, but this is the one that we use the most often in our class. Okay, so the angle that you're going to do in the cosine is going to be opposite of your R value. So let's take a look. If we scroll back up, how do I scroll back up? Okay, if we scroll back up and we take a look at this, in these cases, this would be beta. this would be beta. In these specific cases, since it is a right triangle, that would end up, cosine of beta would end up being 0, and the term would fall out. But assuming beta is not 90 degrees, we're going to have a different value for that. And it's going to change our value for r. The second law that we looked at, actually, let's draw in a little triangle. So let's say component force. So in this case, it would actually be like that to be our triangle, right? Forgot to go head to tail. So our second component force is going to be there, and then our resultant would resist that or go against that. So in this case, this would be B. Let's try to see if we can get a better one. B, this would be R. Let's say this is P and this is Q. You could switch them if you want, but I want to just have something there so that we can now go on to part 2, our law of sines. So with sines, let's name 2 more our other 2 angles. I'm going to name them A and C. So our law of sines is going to be a proportion of a side length or force magnitude over its opposite angle. I'm sorry, the sine of its opposite angle. What does that mean? It means that in the case of the triangle we wrote above, let's start with R and B because they're in a different color. It makes them a little easier to stand out. R over sine of B is going to equal P over sine of its opposite angle, which would be C, which would equal Q over sine of its opposite angle, which is A. So as long as we have we could have 2 unknowns and still solve for this, right? Because we technically have 2 equations, think an equation there, an equation there. So we can solve for 2 unknowns if we have them. Likewise, since it is a proportion, we could also say sine of B over R equals sine of C over P equals sine of A over Q. My advice for this is you want to have your unknowns in the numerator just because it makes it a little easier to solve for. Okay, where does that put us? We're getting bigger as we go down. We're getting like a wide triangle effect here. Okay, so when we are doing, let's stay with we're not in equilibrium conditions. So when we are working not in equilibrium conditions, how do we handle the XY component method? Okay, so XY component method, not equilibrium. How do we do this? So my advice here was to create a table. So let's say we have a point there. Let's go to okay. So I'm going to say F1, F2. Let's not. Let's make one of these forces in a different direction. Okay. Okay. So we have F1, F2, F3, and F4. So I usually go about this by creating a table for my values just so that I keep them all straight. Not required, just make sure that if you don't keep a table, you make it obvious what your answers are. Okay, so for my table, I'm going to put F1, F2, F3, and F4. Oh no, what's going on? And F4. Okay, so the magnitude of these forces is going to be, there's going to be some series of unknowns, right? So we're going to have a magnitude, we're going to have an Fx and an Fy. Okay, so the magnitude is going to be the value as a whole. The x is going to be the x component and the y is going to be the y component. We talked about that a standard, so if we're working in quadrant 1, this is quadrant 1, right, where x is positive and y is also positive. We have forces here. Well, let me step back a minute. Okay. Let me also assign values. So let's say F1 is 100 newtons, F2 is 50 newtons, F3 is 100 newtons, and F4 is 10 newtons. Okay, so the easiest two to figure out here would be F1 and F3. F1, the whole force is occurring in the x direction. Not the clearest in the picture, maybe it's a little crooked, but it's supposed to be. So F1 is going to have 100 as its x value and 0 as its y value. For F3, it's 100% in the y direction. So we're going to say 0 in the x direction and 100 in the y direction. F2 is a little bit harder, but we're going to get this angle here, theta. Let's say theta equals 45 for this case. What we're going to find is if we follow our trig, well, we were also given these equations, but let's solve it anyway. Sine of theta equals, sine equals opposite over hypotenuse. Opposite being the one that's not touching it, so that would be this side, which would correlate with Fy. So it would be Fy over the magnitude of F. So then Fy would equal F magnitude, which would be 50, times sine of 45. Our cosine theta, or cosine 45, would equal, cosine equals adjacent over hypotenuse. Adjacent is going to be this one, is going to correlate with your x value over hypotenuse is your force magnitude. So Fx equals force times cosine 45. So I mentioned in class that we can do this. Whoops, dropping things. We can do this as long as the angle that we use is from the x-axis. If your angle is from the positive x-axis, then you can use these equations where Fx equals F cosine theta and Fy equals F sine theta. Where it gets difficult is if we were to get a different angle. So let's say for F4 over here, let's say F4 is 15 degrees below the negative x-axis. In order for us to use these equations, oh no, where'd they go? In order for us to use these equations, we'd have to use the absolute angle, which would mean we would have to add 180 degrees because we go from the positive x-axis to the negative x-axis, and then we're 15 degrees below that. So we would have to do, in order for that to work, let me fill these in first. So this would be 50 cosine 45, and this would be 50 sine 45. So for our y value, if we wanted to follow that same type of thought, I'm going to zoom in extra so I can try to improve the handwriting there. We could say 10 cosine 180 plus, I think it said it was 15. So 180 plus 15 is going to be 195. So if we did this, and then our y value would be sine of 195. If we did that, that would solve any issue with getting our signs right. So 4 obviously is going to be a negative x value and a negative y value because it is in the 4th quadrant down here, right? Okay, so if you're somebody who prefers to work with triangles and figure the trig out, let's take a look at what that triangle would look like. Over here, we can go over here. Okay, so this is 15 degrees, not to scale, obviously. So this here is going to be our fx axis. This is going to be our fy axis, and this is going to be our f axis. So let's say we want to go with sine of 15. Sine equals opposite. Opposite is fy over hypotenuse is f. Cosine of 15 is going to equal the adjacent, which is the fx, right? Because it touches that angle. Fx over f. So in this case, it didn't change the value, but sometimes say, what if they gave you this instead? It would switch your sines and cosines. But zoom out a little more. Okay. So fy equals f sine 15. So that's going to get us the magnitude of f of y. However, if we are in quadrant 4, our x and our y values are both going to be negative. So this is going to have to be negative. And then this one, f of x, equals f cosine 15. You're also going to have to manually add a negative to this one just to make sure that it, to account for the fact that we're in that quadrant, right? So the other options for our equations here would then be negative 10 cosine 15 and negative 10 sine 15. Okay. They should get you the same value. It's just which way you prefer to think about things. Okay. Let's erase everything and then go in with our, let's not erase everything just yet. Okay, so if we are not in equilibrium, sometimes you'll have unknown values in here, sometimes you won't. But let's say that you had all the known values you needed, but you needed to solve for a resultant force. You don't know the resultant force magnitude. Well, we can find the x component. Let me erase some of the stuff underneath it. Some of this mess. Okay, delete that too. Okay, so our x, or the, my bad. The x component of the resultant force is going to equal the sum of the f of x's. The y component of the resultant force is going to equal the sum of the fy's. So in this case, I don't have the math all done out, but you can do your arithmetic and add, and you'll end up getting, let's say these all added up to, we're gonna have a positive x and a positive y in this case. So let's say we ended up getting that this was, I don't know what it is, so I'm just making up just to continue the lesson without doing math. Um, mm, let's not do that. Let's do 120. 120. Okay. So then R, the vector of R is going to equal 150 I. Let's say that's what they sum to, right? Plus 120J. That's good. That's a start, but it's not our final answer. Our final answer is, so first we need to find the magnitude of R. The magnitude is going to be the square root of the sum of the squares, meaning the square root of each term squared and added together. So the x element squared plus the y element squared, take the square root of that. That would be your resultant force magnitude. Your direction is going to be a little bit different. So in this case, it's an easier one because we have two positive values. So our force would be going somewhere near around that direction. That would be where R went. We want to find this theta. Our x element is going to be, our x element down here is going to be 150, and our y element is going to be 120. Tangent, theta equals opposite over adjacent. Opposite, the one not touching it, is 120 over adjacent is 150. So we could do theta equals the inverse tangent of 120 over 150. I think I might need a thicker pen. But that would get you the angle. My one, how do I say this? My one, it's not a concern, it's just a, be careful. My one caution, I guess, would be, let's say we had two negative values here. Then our force, our resultant force would be going in the negative y and negative x directions, right? We're still going to get a triangle depending on how you draw the triangle. So like, let's say I drew it, let's say we drew it this way, right? So this is our triangle now. So this is our resultant force. This would be its x component, and this would be its y component. Okay, this would be a theta. So we could do still that equation to get this theta, but we would have to then remember to add either to say that, so we would either have to specify that it's at theta and specify the direction, which you could do like that, or you can add 180 and say it's 180 plus theta from the positive x axis, or you don't have to specify from positive x axis as long as you're doing an absolute angle in that case. Okay, let's get rid of all of this and then go to our our equilibrium condition questions. Okay, So now, equilibrium conditions. Triangle rule 1, parallelogram rule. So your triangle and your parallelogram rules are going to be the same in that you're going to have a three-sided figure or you're going to have a parallelogram. So for triangle rule, why did I name these two and this one? That's confusing. I think it should be switched, but it doesn't matter. Irrelevant. The point is, for equilibrium triangle rule, what we're going to end up having for equilibrium triangle rule, we're going to have three individual forces. Three individual forces that have the sum of the forces is equal to 0, right? That's what our equilibrium condition is that resultant, which is the sum of the forces, is equal to 0. This also means that the forces are going to create a closed polygon. In cases where we have three forces, it's going to give us a closed triangle. So let's say we have this point here, we have an X, a Y, and then a combination force. This kind of looks like our X, Y, and Z axis, but, you know, not on purpose. So let's say F1, F2, and F3. So then in our triangle, we're going to connect them all head to tail. So let's start with F2 in this case, then F1, then F3. You see they all go in the same direction. It's all going clockwise in this case. Okay. Again, I gave you an example with a 90-degree angle, but that's not always that's rarely gonna be the case. What else do we have to say here? Yeah, so the triangle rule and parallelogram rule are essentially going to be the same, except for that, well, let's get rid of this parallelogram rule here. You're going to go with the triangle rule for equilibrium conditions. You're going to go with those same equations, so your same law of sines, law of cosines equations, except for you would replace your resultant force with your maximum magnitude force. Okay. I don't want to say R equals that because it's not true. R equals 0. R equals 0 in the X direction and in the Y direction. The only difference for equilibrium, for XY component method in equilibrium, is that after you have your table with your force, your magnitude, your X element, and your Y element, so let's say we filled this up with our F1, F2, F3, F2, F3. Usually, in these cases, there's going to be something missing from your chart. But you're going to know that they equal a resultant force with a 0 magnitude, a 0 X element, and a 0 Y element, which then gives us two equations to work with. One is that sum of the forces in X equals 0. So, equals F1X plus F2X plus F3X, and summation of forces in Y equals 0, equals F1Y plus F2Y plus F3Y. And then, of course, when we're working with tables, XY component method, we don't have to, where was I going with that? We are not topped off at 3 forces. We could have more than that if needed. All right. Let me know if you guys have any questions, and I will be talking to you soon. All right. Thank you.